In this problem, we have 2 points, points A and B, both located on the x-axis. Point A is located at x equals 0.60 meters, and point B is located at x equals 0.90 meters. The absolute value of the potential difference between the 2 points is given. It's 240 volts. And we are also told that the electric field, so this is a uniform electric field region, and the electric field is pointing in the negative x direction. Part A is asking which of these points is at the higher potential. Now remember, electric field vector points from the high potential point towards the low potential point, or in other words, it points downhill. So point B is at a higher potential. So V sub B is greater than V sub A. In part B, we're calculating the value of E. How is E related to the difference in potential? Let's remember the formula. VB minus VA is equal to the negative of the line integral of electric field E over the path from A to B. So let's apply that to our problem. In this problem, we have a uniform E parallel to the x-axis, so that dot product in the formula is just going to be equal to negative E times dx. Now, why negative? That's because the electric field vector points in the negative x direction. So E dot vector dx is going to be negative. The angle between the electric field vector and the unit vector along the x-axis is 180 degrees. Now the two negatives cancel. So let me rearrange this formula, simplify it a little bit. Two negatives canceled on the right hand side. I also pulled out E because E is constant. Now what's the integral of dx? That's simply equal to x. And then we evaluate it from A to B, like so. And what is that equal to? It's equal to x sub B minus x sub A, like so. Now we're looking for E. Let's isolate E. E is equal to V sub B minus V sub A, that's the potential difference from point B to A, divided by XB minus XA. Now let's go ahead and substitute the numerical values to calculate the final answer. Now remember, point B is at a higher potential compared to point A, so VB minus VA is then positive 240 volts. And then in the denominator we have XB, which is 0.90 meters, minus XA, which is 0.60 meters. Those are given. And when we do the calculation, we find that the electric field magnitude is equal to 800 volts per meter. Here I'm using scientific notation because I'd like to keep two significant figures to be consistent with the numbers given in the problem. In part C, we have a particle with some negative charge moving from point B to A. And the question is, what is the work done on this particle by the electric field? Work done by the field is equal to the negative, the change in potential energy of the particle. So change means final minus initial. In this case, the particle is moving from point B to point A, so that's going to be U sub A minus U sub B. And I also have this overall negative sign coming from the formula, so I'm going to switch the order to get rid of that negative. So work done by the field on the particle is equal to the particle's potential energy at point B minus the particle's potential energy at point A. Now, how can I calculate the particle's potential energy at a certain point? Well, by definition, the potential energy at a given point is equal to the charge of the particle times the electric potential value at that point. So U equals Q times V. So let me go ahead and substitute. So here I have an expression for work written in terms of the particle's charge and the electric potential at points B and A. Now Let me factor out that Q, that's a common term, and then I will substitute the numerical values. Substituting the numerical values, we find that the work done on the particle by the electric field as the particle moves from point B to A is equal to negative 48 microjoules. This is negative work done by the field, so that means the particle is gaining potential energy.